Okay, welcome back to the workshop. I'm going to continue with the module that we were working on yesterday, which was discussing how to build an ODE model of viral infection and immune clearance using Tellurium. And last time we had launched Tellurium on NanoHub, and we had begun working with the Tellurium code. And I want quickly to remind you again of what we did yesterday. The outline here is going to be fairly short, although there are a lot of exercises, and so in principle it could take a long time. We're certainly not going to do all of the exercises that are in this list, but those will all be available to people who want to explore more. I'm going to talk a little bit about the principles of modeling, addressing some issues that came up yesterday. And then we're going to continue building our model of viral infection and clearance, talking about innate immune clearance and adaptive immune clearance, and show that with some very simple assumptions, we're able to replicate the observed pattern of viral load that's seen in influenza infection in vivo. Again, the workshop resources are on the Google Drive and the Slack, and also the CC3D website. We started out last time by talking about the dynamics of viral infection. There were multiple patterns of viral infection, as measured by the amount of circulating virus in the individual tissue as a function of time, what we called monophasic, biphasic, triphasic, and biphasic decay. The monophasic and triphasic we hadn't talked about so much. We looked more specifically at influenza. Influenza has this classic biphasic pattern, and we were trying to understand that in terms of susceptible cells becoming infected, susceptible cells having a latency before they produce virus, the virus killing the cells, and the immune system coming in and clearing. Reminder on how to launch Tellurium. If anybody's having trouble getting back to Tellurium, please let us know now so we can work with it, you to get back where you need to be. When you're in Tellurium, you should have from yesterday saved the notebook that we used. If not, please take the time now to launch Tellurium again. Remember how to use the open command. Navigate to where you have the notebook saved, and then upload it again. Reminder where Tellurium documentation can be found. And then I want to return to the structure of Tellurium models. So let me just give a quick poll to make sure that everybody has Tellurium running. So the exercise here is going to be have you got Tellurium running, and the old simulations from yesterday. Does anybody need any help getting it back on their screen? If so, raise your hand and we'll get somebody to help you. Looks like pretty much everybody is back where we were earlier. And so I'll continue. I want to remind you that we're going to be using the antimony Tellurium. There's very simple syntax for antimony strings. Tellurium uses a Python string as modification. The one problem with that is if there's a syntax error in the model specification, you don't always get a descriptive error message about where the error was and what happened. But it's otherwise very convenient. We use the triple quotes in Python to indicate that we're going to have a string that potentially has carriage returns in it. We specify equations or rate laws in this very simple format. In this case, susceptible cells become early infected cells type I1, semicolon, and the rate law. We name the equation or name the rate E1. That gives us access to the value of beta times T times V. We specify all of our parameters, initial conditions, and so on. We use these comments, parameters, inputs, and initial conditions, but those are completely optional for you. You don't have to use those formats if you don't want to. And then to load the model for execution, we use the Tellurium method TE load A, operate on the model string. And then to simulate it, we use the method m.simulate, initial time, final time, number of steps. And the output of m.simulate is an object that contains the names of the variables and the time and the values of the times that were simulated. There's this convenience function m.plot that throws up a quick plot. You'll see a little bit later if you want. Well, in Herbert's class, you discussed in some detail how to plot using matplotlib. We're going to be moving into CompuCell, which has slightly different plotting, and so we don't want to get too involved in the plot routines for Tellurium at the moment. Any questions and reminders on how to use Tellurium? Okay. The key thing again in Tellurium is going to be specifying rate laws, and in this case, we were specifying the rate of infection. T goes to I1, rate beta times T times V, and that's really all there is to it. One thing you have to remember is that if you have T goes to I1, that rate term is going to show up in two equations with mass balance. That's very convenient if you have complex chemical reactions like 17H2 plus 15O2 plus 26C goes to something. Tellurium will automatically handle stoichiometry. When we're doing population models or phenomenological models or regulatory models, that geometry function isn't used as much, but it's helpful to remember that it's there. The simulation results are an object, again, that contains column names, so the variable names for each column, and then the values at each time step. And that's something that you have access to. I can use classic Python slicing to manipulate those arrays if you want to do fancy things. Again, for this class, we're not going to use those fancy functions very much. The one thing that we have been doing, which I want to remind you of, is that you can, when you run the simulate function, you can select the columns you want to have output by putting at the end of the simulate call, comma, and then a list of the variables that you want. The variable names go in quotation marks, and time is a reserved word that specifies the time step value in the simulation. If you don't put the time in when you request a limited number of variables, it won't give it to you. So if I put 0, 10, 100, square bracket t, I1, I'd get a column of t and a column of I1, but I wouldn't get the times. That may or may not be what I want. So usually we're plotting things against time, so we need to get the time value out. We also built this little simulation function for doing a parameter scan. In this case, we used range. I tend to use arange myself, more numpy arange. For p in range, 0, 6, 1. Remember that will go from 0 to 5 in Python syntax. We reset the simulation, m.reset all. You can also use m.reset, which resets just the time and not change parameter values. And then we use the assignment feature, m.v resets the initial value v in simulation. And then we rerun the simulation. We use m.plot with show equals false. Show equals false tells us to overlay the plots one on top of each other. And then we use te.show to show the plot, which has all of the data sets put on top of each other. So that's a very simple way to do parameters. The other thing that we did in a fair amount of detail last time was to look at this experimental viral load curve for influenza in mice. And we saw that there were actually 5 regimes in this viral load curve. A short initial period called an eclipse or latency, during which no virus is produced by the cells because it takes time for the virus to replicate and assemble itself and be released by the cells. A period 2, where you have rapid exponential growth of the amount of virus in the tissue. A saturation time 3, which happens around 1.5 to 2 days in the case of influenza, when the amount of virus in your body is maximal. Typically, you don't start feeling sick until that peak. That illness that you get, the fever, the headache, all of those things are typically associated with high levels of interleukin-6 in your body. So by the time you start feeling sick with the flu, the virus has already peaked or just about peaked. Then a period of exponential but relatively slow decay, where it takes about 5 days for the amount of virus to go down by a factor of 10. That's mainly due to a variety of innate immune responses. And then starting around day 7, a rapid exponential decline of the virus, about a factor of 10 to the 5th over 2 days until the virus is eliminated. So we built a model of the infection part of this, not including the immune response, in which the virus infects the susceptible cells. Those susceptible cells become early infected cells. Those early infected cells, after an eclipse time, become late infected cells, virus-producing cells. Those virus-producing cells release virus into the environment. We can write that schematically as T cells go to I1 cells at a rate proportional to rate of infection per cell per unit of virus times the amount of virus measured in TCID times the number of infectable cells. The I1 cells go to I2 at a rate K, which is 1 over the eclipse time. And the infected cells, I2 cells, produce virus here at a constant rate of P per cell per time, per day. We can put that simulation into a Tellurium. That's where we ended last time. I was putting that simulation in, and we ran it with a little parameter sweep, and we saw that we got something that looked like this, where we have a short eclipse time. It's hard to see it because it's very short, followed by a rapid exponential growth, followed by a slow saturation. And I'd like everybody to come back, if possible, and run that simulation just to get back on the same page. Okay. Remember to run a Tellurium cell. You can hit Shift, Control, Shift Enter or Control Enter, or you can go up in the Tellurium menu under Cell and do Run Cell. Javier, could you just ask to check to see if everybody is caught up to that using the poll? Just let's make sure everybody's caught up. Okay, looks like people are pretty well caught up. If you have any questions, our team will be happy to help you get caught up. Looks like we have almost everybody caught up. give you just another minute to see. If there are any specific problems, please let us know. We'll be glad to help. If something turns into a major problem, we can always put you in a breakout room where you have the ability to screen share, talk to people, and so on. Just let us know. Thanks again to Javier for being the mastermind for running the Zoom today. Okay. So now that we have this basic model, I want to remind you of what we saw, which is that of a period of about a day in this case, we see that the population of uninfected cells goes down to 0. Everybody's infected after a day. The population of early infected cells comes up, peaks around a day, and then decreases to 0. And the population of uninfected cells is basically, of course, 1 minus the others. And so that starts out at 0. It starts coming up around 3/4 of a day, and it reaches 1. All of the cells are late infected cells around 2 days. And so that's the time course of evolution of this particular line. If we compare the curves and look in a little more detail, put it on a log scale and look in a little more detail, we see that there's a latency indicated by this blue line here and this exponential growth. And we can compare that with the level growth that we see in our data set. They're actually the parameter values we've used here, which we just eyeballed, are actually pretty close to the ones that work. So we can now explore a little bit how the parameters beta, k, and p change the exponential phase of the growth. I don't want to go through all of these, and we already did the rule t plus v goes to I1. But let's just remind ourselves how to do the parameter sweep. Here we were sweeping the value of k for the eclipse phase. We also tried sweeping the infectivity, beta, and in that case we were using logarithmic scaling, so we were multiplying by 10 to the p. And in that case, we saw very different responses. In the one limit, when the rate of infection is very low, we see this very slow increase of the amount of virus. When the exponential growth is very high, essentially all the cells become infected at the beginning, and everything is controlled by the time it takes to go from early to late infected cells. Notice that with this particular set of equations where we have decay of the virus in the environment, we always reach a saturated state. Any questions about that so far? Everybody able to do that? We didn't sweep the delay time for the conversion from I1 to I2. Let's do that. And let's look at the I2 cells for that. So if we look at the number of I2 cells, if the rate of infection is very low, it takes a long time to get the I2 cells. As we increase the rate of infection, the I2 cells appear faster. Let's sweep the delay for the I1 cells to become I2. Sorry, I1 cells to become I2 cells, that's K. So we did that. Actually, that's the one we did first. So we did K equals plus B. That was this one. Didn't have that big an effect. And let's do the last one, which is sweeping the amount of virus released. And that way we can do it in factors of 10 as well. So let's try that together. We're going to change the parameter P, which is the production of virus per cell. And I understand that it looks a little bit confusing to have P be a variable inside of the model string and also be the parameter that we're sweeping. Fortunately, Python knows the difference between m.p and p, although from our point of view, that may be a little bit confusing. So let's see what happens here. Looks pretty familiar. If the rate of production of the virus is very low, we have a long time to get to IR1s, I2s. Let's look at the amount of virus. Look at the amount of virus together. And here you get something that looks a little bit different. If the amount of production of virus is very low, which is this bottom one, you don't get a significant amount of virus in the population until 4 days, and then it increases essentially linearly. If the amount of virus produced per cell is very high, it explodes early and basically disappears off the chart. And we could try changing the scale to see what's going on. And why doesn't everybody try running that one little simulation where you're scanning the amount of virus produced per cell and seeing what the effect is on the total viral load? Everybody take a minute to try that simulation, and then when you're done, we'll come back. There are actually a lot of things one could do with simulation of this kind. Already, there's some non-trivial results that you could obtain with a simulation. We're not going to have time to explore those here, but I encourage you to think about those as you go forward. Somebody says, what is 0, 10, 100 doing in Simulate? 0, 10 tells you how long the simulation runs. I don't have labels on this axis here. I should probably have included some labels. But the x-axis, as you'll see in my graph, goes from 0 to 10. Remember, we specified things so that the time is measured in days. And so m.simulate 0, 10 says to simulate for 10 days. The next number, 100, says how many discrete time points do I want to use in my numerical approximation of the ODE solution. So it tells me that my time step in this case is 10 over 100, or 1/10 of a day. So I'm making time steps of 2 hours. That works because the variables aren't changing very rapidly. If I had a more stiff set of equations, I would have to take that time step down to be smaller. And if I had a very stiff set of equations, I might have to use different solvers, implicit solvers, instead of explicit ones. Okay. So our whole model looked like this so far. The T's became I1s, the I1s became I2s, and the produced virus. And one thing that we did not include here is the fact that the virus has a finite lifetime. In tissue, the virus is broken down, it decays. This is something we know pretty well, not outside of tissue, in the sense that if you're worrying about COVID, there's been a lot of discussion about how long SARS-CoV-2 virus remains infectious, whether it's up in the air, on a surface, in clothes, on food, and so on. And so we know that virus particles break down in time. If they dry out, they may become non-infectious. If they're exposed to bleach, they become non-infectious. And your lungs and your other tissues have a variety of enzymes in them, for example, RNases, that break down components of viruses. And they're pretty good at that. In fact, the barrier function of your skin and your lungs is very good. It keeps out the vast majority of viruses and bacteria that are trying to attack. And so only the number of viruses that actually get through those barriers is quite few. Unfortunately, you only really need one to get through to get sick. And so the extracellular virus has a lifetime. It doesn't stay there forever. We're going to include the fact that that virus has a lifetime. We're also going to say that clearance can happen for a variety of reasons. And probably tomorrow we're going to investigate one of those reasons. The virus can be broken down by enzymes. It can be gummed up and made non-infectious by antibodies. The cilia in your lungs are actively trying to push the virus out of your lungs. One of the reasons when you cough, you're infectious, is that the virus is actually being pushed out of your lung. And there also, at least for some viruses, are macrophages and neutrophils that actively phagocytose, that is, eat and break down the virus. And we are not including macrophages and neutrophils explicitly in this model, but tomorrow we're going to work with you on the fly to try to develop a little model of macrophage viral scavenging, macrophage phagocytosis. For the moment, we're simply going to assume that there is some lifetime for the virus, and experimentally, that lifetime is a couple of hours, and we'll set that number to be 2.5. And remember that whenever we set a lifetime, the rate constant is the reciprocal of the lifetime. And so if the lifetime is 2.5 hours, well, 2.5 hours is about a tenth of a day, and that means that the rate is about 9.4 or 10 per day. And so we're going to add a term that the level of the virus, the EDT, we had P times I2 is the production, minus C times V. And so I'd like you to go in and add a decay term to your equations. And this is going to have to be done. I'll let people think about how to do that for a second. How are you going to add that in the context of tellurium antibody? There are actually two ways to do it, one of which is ODE-like and one of which is antimony-like. And I'll give everybody just a minute to think about how you could add decay of the virus to this model here. Remember that E3 is specifying the creation of the virus. So I'll poll you to just ask if you've thought about how to do that. And if you don't want to try it on your own, it's okay. You can wait for me to show you how I did it. But there are many ways to do it, not just the way I do it. So there were some questions. I missed a question. So somebody said, why biologically do a parameter scan with additive steps for K, but exponential steps for beta and P? Well, K is a time scale, a delay, and we know that the time constant K was the amount of time it took for the I1 cells to become I2 cells. That time can't be very fast. It can't be more faster than about 2 hours because of the mechanics of viruses. And we also know that it can't really be very slow. It can't take more than on the order of a couple of days. And so we know that the range of Ks would be the reciprocal of that. The range of Ks that are possible is not so big. On the other hand, the affinity of a virus with a receptor can vary by several orders of magnitude. And so in the case of the affinity of a virus for a cell, which is our beta, that can vary by multiple orders of magnitude. And so that was the reason I picked an exponential scan for one and a linear scan for the other. But absolutely, you should check both. There's no reason you shouldn't check the exponential scan for one, and if you find an interesting parameter regime, going in with a linear scan in more detail for the other. Good question. There was also a question about mass balance. And when you're writing chemical reactions, you always are worried about mass balance. The world does conserve mass in chemical reactions. In the equations that we're writing down here, T goes to I1 is mass conserving. I1 goes to I2 is mass conserving because the cells keep their identity as they go through those transitions. However, the production of a virus modeling the chemicals that are being used up to make the virus, and therefore the production and elimination of the virus don't have to conserve mass. And so that's a good question. When do you conserve mass and when you don't? That's something that we'll have to think about again and again as we go through this. So I don't know how people did it themselves. There are two basic ways that I could write this equation. I could either write that the creation of virus is the creation rate minus the destruction rate, like that. And that would be very ODE-like. It would be thinking about E3 as dV by dt equals P times I2 minus C times V. Or I can do it the reaction, which is how I'm going to choose to do it, which would be to say before the virus goes to nothing, as somebody already suggested, and the rate of that is going to be V times big V. I better not call it V, C times V. And then I have to define my parameter value. C equals, we said 9.4 per day. Clearance. And let's see what happens when I run that. Let me get rid of the parameter scan here, and I'll just do an MDOT simulate and plot by itself with no parameter scan. And I'll plot everything the first time. Okay, so what do I see here? Things look a little bit different now. The virus has still has a latency. It still goes up exponentially, but instead of continuing to increase but at a slower rate, it reaches a hard saturation at 10 to the 6th. Did everybody get that result? If I do the parameter scan, I'm going to see things that are a little bit more. Actually, the parameter scan doesn't look that different from the previous one. But now my saturation is basically giving me a flat result. All right. And I should say, if I scroll down through this deck, I've been working in this cell at adding things step by step. But in fact, all of those steps are written out in the deck, if you want to look at it. All right. And so now we can get the first three phases of our viral load curve. We can get the latency, the exponential increase, and the saturation. And we said that the saturation happened at 10 to the 6th, and that is in fact what we see. What we see here, our saturation, well, our saturation here for V is at 10 to the 6th. Our exponential increase is a factor of 10 to the 6th over a little over a day. It's a little slower than the one in the experiment. And the latency is perhaps a little bit shorter. So we could tune our parameters to make this agree a little bit better with each other. but we're pretty close. Okay. The next thing that I want to talk about, I'm going to skip the next exercise. You can do that on your own. The next exercise would be to look at what controls that level of saturation, that 10 to the 6th value for the viral loaded saturation. We can think about that pretty straightforwardly just by thinking about how things will behave. If I increase the clearance rate, C, then clearly the amount of virus will go down. If I increase the production rate, P, the amount of virus will go up. If I increase the number of infected cells, I2, then the amount of virus will go up. But I can write down immediately what the saturation level is. The saturation level, looking at these equations here, is going to be P times the number of infected cells. At the end, they're all infected, so that's T0. P times T0 divided by C is the saturation level of the virus. It doesn't depend on any of these other constants. It doesn't depend on beta, doesn't depend on K or D. Just P, the total number of cells, and the saturation level. Now, we've all done all of this so far, assuming that the cells don't die when they're infected by virus. In fact, the cells do die when they're infected by virus. There are some viruses that are called lytic viruses that actively kill the cells when they're released. So in a lytic virus, the cell becomes infected, the virus replicates inside the cell, and the only way it gets to the outside is by having the cell actually burst open and die to release the virus. Diseases like viruses like influenza and SARS-CoV-2 are not lytic viruses. They actually use the secretory apparatus of the cell to be released, the same things that the cells use to secrete chemicals that they want, called exocytosis. And that means that producing the virus doesn't by itself kill the cell. However, a couple of things do go on. One of them is that the virus doesn't have a mechanism to regulate how much of itself it's being produced. And the amount of virus in the cell actually goes up exponentially. And so after a day or two, the cell is using up essentially its entire energy budget and its entire set of biochemical resources producing virus. And that in itself is a stress on the cell that usually will kill it. The cell also has a variety of antiviral recognition systems that operate at the molecular level that can lead to apoptosis of the cell. When cells recognize that they're infected, they can then decide to go through programmed cell death or pyroptosis, another kind of programmed cell death. And thirdly, there are a variety of immune system responses that come in and kill infected cells. Some of those are non-cellular. Some of them, like some DAMPs, some of them and trail signaling. Others are cellular, but not using specific recognition motifs. So, for example, natural killer cells can come in that are resident in the tissue, can come in and kill infected cells. And so we're going to sweep all of that complexity of the innate immune response under the rug with a single parameter. And that single parameter is going to say that the late infected cells, the ones producing the virus, die at some rate D. Now that's a pretty harsh simplification because we're putting a lot of different death mechanisms in play. And some of those death mechanisms are very important and may actually make the difference between surviving an infection and not. But for the moment, we're going to lump them all together as a single term. And it's going to be interesting to see whether that harsh set of approximations works or not. But we're now going to add the fact that our I2 cells here can die, and that death rate is going to be a constant rate per I2 cell per time. And we're going to assume here that the lifetime of the infected cells, in the case of influenza, is about 4 days, which gives us a death rate of about 0.24. For SARS-CoV-2, it appears that lifetime for an infected cell is about 2 days, so it would be about half. I should say that I believe, and somebody can check this if you like, that experimentally influenza cells don't live quite that long. Once a cell is infected by influenza, it lasts about 12 hours or a little more. And so then we'd be using a d-value of 2 instead of a d-value of 1/4. And that's something we'll check just now. So what I'd like you to do now is put into your equations this extra term. We already looked at how to add the clearance of the virus. Let's go together and add clearance of the immune cell, of the infected 2 cells. And this is going to give us something quite different from what we had before. What's going to happen, for example, to our viral load now when cells die at long times? Try thinking about that before you do it, but let's do it together. Add E5, I2, you should do it your own way. I'll type I2 goes to nothing. Sorry, no, to D. I'm creating a class D. And the rate is going to be D times I2. So I'll have death of the cells by innate immune response. I have to give my parameter value, D equals, we'll start with 0.24. Units out per day. And we'll say that the initial number of dead cells is 0. Okay. And let's run that. So what happens? First, let me relaunch the poll and see if everybody's able to get that to run. Are people able to run that? Probably plotting the viral load and the number of dead cells on the same plot isn't ideal, but we could change the plots. Give people just another minute. I appreciate your patience with the squeaky chair. I don't know why the chair decided to squeak today. Must have known I was recording the session. Okay. I can show you how we did it here. And when I run it, I get something that looks like this. Let me put this on a linear scale so it's comparable to what I had. It looks sort of different on a linear scale. What I see again is this rapid peak of the early phase that's not affected by the death. the I2 cells come up and then decay. The amount of virus is much lower than it was before, and it comes up and then it goes down. And of course, once the cells are dead, they stay dead, so they don't come back. Log scale. I see this rapid increase in the viral load followed by the slow decay. So now I've got region 1, eclipse, region 2, rapid exponential growth, region 3, saturation, and region 4, slow exponential decay. And those all agree within a factor of 2 with what we see in the experiment. So just pulling the parameters out of the air, essentially, we got the right results. Let's try something else. We said that in reality, perhaps the cells die faster than I put in here for the flu. So I've gone from 0.24 to 4, actually 2, factor of 0.24 to 4, factor of 8 difference in lifetime of the cells. Let's run that and see what happens. Doesn't look that different. The peak amount of virus is a little bit lower. The cells die much faster. And so all of my cells have died by 2 days in this particular simulation. Let's see if we compare them. Let's run this one and one where we've got the other value. You work out how to do that all the time. Everything you need is here. Do a reset all, and then I'm going to change the value E. I'll put it back to where it was before, 0.2. Here. And now I can compare the two. Notice that up to 2 days, they look very, very similar. But my viral load peaks a little bit lower. It peaks at 510 to the 5th instead of 10 to the 6th. And the decay is much faster. It goes down over a period of about 8 days. It's gone back down to 0, essentially. Whereas in the other case, after 8 days, it's only down by a factor of 10 compared to its earlier value. Were people able to get that to work? Okay, great. Okay, so I'd like to talk a little bit about some principles of modeling. There's always a tension in a workshop like this about what you want to cover, how much theory to do, how much mathematics to do. Everyone has different background. We tend to do, as the years have gone on, we've given more and more of these. We give less and less mathematical and physics detail and more hands-on exercises and practical results. The reason for that is that we found over the years that you put mathematics up on the board, people fall asleep. If you put theoretical considerations on the board, people start checking their email. We certainly don't want you to be bored or to be to fall asleep. But I do want to talk a little bit about some principles of modeling that are going to come up again and again as we go through this course, which is that we've written down a lot of rate laws and transition rules. And we didn't have any experimental data to base those on. And so we're going to run into this a lot, that we're going to have to guess, or at least come up with reasonable hypotheses for rate rules. In the case of chemistry, we have both some physics-based and some empirical but well-validated rate laws. And if you took Herbert's workshop last week, you'll have heard a lot about rate laws. And I'll I certainly recommend looking at Herbert's textbooks on rate laws, chemical reaction kinetics, for a lot more detail than I'll be able to talk about now. For the people who heard Herbert's workshop last week, this will be a bit of a review, but I do want to talk about that a little bit, because in the case of chemistry, there are objective reasons why you have mass action kinetics, Michaelis-Menten kinetics, and so on. In our case, these are phenomenological. There aren't first principles rules for why rate laws have the forms that they do, but there's still some simple mathematical ideas that you can use to justify what we're doing. The most important thing to think about, and this is something you should do when you're building any model whatsoever, is to think about what we call limiting cases. In particular, what happens to the rate when the population that's acting, which is participating in the rate, reaction, or the transformation, is either very small or very large. And the next thing you're going to think about, again, is going to be limitation. So the first thing we're always going to think about when we think about a rate law is what happens when you don't have something or you have a very small amount of it. That's called limiting case lower bound. And so the first thing you should do whenever you think about what a rate is ask the question, if I either have a very small amount of the thing or none of it, what's the rate? In the case of a transition rule like I1 goes to I2, it's clear that if I have no I1, my rate of conversion of I1 to I2 has to be 0. If I had a non-zero rate and I had no I1, then I'd wind up with a negative amount of I1, which I can't have. The same thing, of course, if I have infection. If I have no uninfected cells, I can't infect them, and therefore the rate of infection has to be 0. If I have no virus, the rate at which the cells become infected by virus has to be 0. And so in general, for the kinds of rate laws we're dealing with, at 0, the rate has to be 0. The second question is what happens to the slope of the rate law at 0? Is the slope 0 at 0, or is it non-zero? For most of the things that we're going to deal with, it's not true for gene regulation, but for most of the other cases we're dealing with here, for example, it makes sense that as we increase the amount of I1, at least for small amounts of I1, the rate of conversion from I1 to I2 would increase. In particular, because we're talking about I1 going to I2 is a process that's happening individually with cells, we'd expect that the rate of increase would be linear. And so in most cases, we're going to wind up with something where if it's a rate law that applies a single argument, the rate increases with the value of the argument. And at least for small values, it increases linearly. If the slope at 0 happens to be 0, then you're going to get Hill-like equations. It's a little bit different. But just knowing that at 0, the rate is 0, and that the slope at 0, the rate law is non-zero, gives you the basic phenomenological rate law. So if we have a generic rate law, which is we have some species x, and the rate is f of x, then we do a little bit of mathematics. We Taylor expand f of x around x equals 0. And the first terms of a Taylor expansion are f of 0, x times f prime, evaluated at 0 plus 1/2 x squared f of the prime, and so on. We've said that the value is 0 at 0. That means f of 0 is 0. So f of x is equal to x times the derivative of x of f at 0. And we've said that that's non-zero. And in that case, that first term is the biggest one. And so as long as x is small, f of x is approximately x times the slope at 0. If the slope were 0 at 0, then those higher order terms would come in and we'd have something more complicated. But to begin with, as long as that slope is non-zero at 0, as long as the rate is not 0 for very small values of x, we're going to get f of x is approximately linear. And that's what we call first order kinetics. And in our equations here on the right, we have used it 1, 2, 3, or 5 times. If we have two parameters or two variables, things are a little bit more complicated. We can Taylor expand around x and y. In this case, x could be the amount of virus and y could be the amount of number of susceptible cells. We get a bunch of terms. The first term is 0, f of 0 comma 0 is 0, because we've said that our value is 0 when things are 0. The second term is 0 because it's independent of y. And we want this to be 0 no matter what y is. And so that means it has to be 0. The same for the third term, and the same also for the first and third terms inside the second order equation. And so the first non-zero term that we're left with is this one, 2 times xy, e squared f by dx by dy. And that means that to lowest order, f of x comma y is xy times the second derivative at 0. And that's exactly this bilinear form, beta times v times t. And that kind of equation is known as mass action in chemistry. Fundamentally, what it's saying is if I don't have any virus, I can't infect my cells. If I don't have any cells to infect, the virus can't infect either. Now, if I want to do something fancier and expand in higher order, this becomes something called a Hessian matrix. And there's a simple linear algebra equation that gives you how the higher order terms work if you want to do Hill equivalence in that case. But that's the argument for why you have linearity in these terms. We're now going to be thinking about upper bounds, and we're going to make a few upper bound cases. We're not going to go into the details of why we made those choices, but I want to give you a little bit of background on that. So now we're going to think about what happens when one of our values is very large. In the case of I1 cells going to I2 cells, the I1 cells are making that decision one cell at a time. I have 10 times as many I1 cells. I expect to be getting 10 times as many I2 cells. There's nothing that should change the rate from being linear. On the other hand, there are plenty of situations in which you do expect the rate to saturate. For example, think about viral infection. If I have a cell and there's a small amount of virus in the environment, then I expect the rate at which that cell becomes infected to go up. On the other hand, the infection goes through receptors on the surface of the cell, and there are a finite number of those. And so even if I have an enormous amount of virus in my environment, it can't bind to the cell faster than the virus can attach to the receptors. You can't have more virus attached than the number of receptors. And once it's attached, it takes time for the virus to internalize. And so the fastest rate at which cells can be infected when there's a lot of virus is limited by a property of the cells, not by the virus, not by the amount of the virus. And so what we would expect is that in this picture here, if the parameter here is the amount of virus, and the upper value is the rate of infection of a cell by the virus, if I have a small amount of virus, the rate of infection increases linearly with the amount of virus. But if I have a large amount of virus, the rate of infection doesn't depend anymore on the amount of virus. And it's very common that processes that take a finite amount of time cause saturation. And when amount of time is determining things, we call that rate limitation. If I want to write the simplest functional form, it gives me that. I could do the same mathematics that I described before. I won't do it out for you. I've done enough math. That's almost all the math we're going to do in this class. Here I'm saying that f of x is equal to some maximum rate, v, if you took Herbert's workshop, you recognize this one, times k times x divided by k plus x. What is the behavior of this? If x is small, the denominator is approximately k, and so this gives me just kx over k, which is x. So if x is much smaller than k, f of x is approximately v times x. That gives me a linear increase in the slope v. What if x is very big? If x is very big, x is much bigger than k, then I have approximately kx over x, which is k, and the saturation then happens at v times k. And there's a typo here. This should be rate v times k. I can rewrite this by dividing through by k. I get v times x over 1 plus x over k. And so you can see that the saturation is controlled by the ratio of k, x over k. And the value of k is called the half maximum value. When x equals k, the rate is 1/2 of what it is if x is infinite. That has another name. It's called the Michaelis-Menten form. And in chemistry, you see it a lot. But it comes about basically for the reasons that we've discussed. There are other kinds of saturation forms. There are exponential ones, and you can write an increasing exponential. There also are decreasing Michaelis forms. In this case, you replace the x in the numerator by 1, and that starts at a finite value and decreases to 0. And you could have an exponential decay, v times e to the minus k of x over k. Now, if you have multiple, that's for a single variable. If you have multiple variables, you have to combine these saturation terms, and then things get a little bit more complicated because there are multiple ways that make sense that you can do this combination. I could multiply the saturation term in x times the saturation term in y in a variety of other ways. And as we go on, we're going to make some guesses about those saturation forms, but we're not going to go into great detail. We can play with those in the exercise. Okay, somebody says, in enzyme kinetics, Vmax is a theoretical quantity. Vmax is never achieved in experiments. Does this apply too? Well, if x is very large compared to k, then v is approximately, f of x is approximately v, but 1 plus x over k, x over 1 plus x over k is always slightly less than 1. So yes, you're right. Unless x is infinite, you never get exactly v, but you get very close to it. So if x is 10 times k, you're within a few percent of the maximal rate. Good question. Okay. Another case, and this is why I'm bringing this up now, is we're going to introduce T cells that are going to come in and kill our infected cells. They're going to be CD8 plus effective T cells. And each T cell takes about 40 minutes to kill its target. And that means that even if we have a lot of infected cells and a few T cells, most each T cell can kill per day is 30. So no matter how many I2 cells we have, the most I2 cells we can kill is 30 per day, is 30 times the number of T cells. And that means that we'd expect to have a saturation form where the rate at which we kill infected cells is saturated. That is, the K is going to depend on the number of T cells. And if we think about that here, Vmax is 30. That's the most one T cell can kill per day. I2 is the number of infected cells to be killed. And the saturation constant is E. And so we would expect then that the killing rate for I2 cells, immune cells, if each immune cell takes 40 minutes to kill its target, would look like 30 times I2 divided by 1 plus I2 over E. That would be a reasonable guess at the rate law. We're actually not going to use the rate law quite like that. One of the things you could do in homework, and we're not going to have time to do it in class, would be to explore whether you get a different result if you make that assumption. I hope that was a little bit helpful. we're not going to go into a lot of the theory here, but I think it's important to think about how you might build some theoretical, reasonable hypotheses about rate laws. Because in general, they're not to be known. So when you start building models of these problems, you're going to have to come up with hypotheses. And those are things that you're going to run into again and again. If the derivative at 0 is 0, then you tend to get what are called Hill functions. Hill functions are classes of sigmoidal behaviors. They're also Canch sigmoids as well. Hill functions have the same form as a Michaelis equation, but instead of having x divided x in the numerator and x in the denominator, you have x to the n in the numerator and the denominator. And there's actually a typo here because the n should be around a parenthesis. There are different conventions about how you use the Hill coefficient. I prefer to make the Hill coefficient modify x directly inside the n. You'll see this in different ways. Again, k here is the half maximal value. And if I scan different values of the exponent, what I see is that for the exponent of 1, I have my Michaelis term, this one. If the exponent is greater than 1, I see a set of increasingly steep sigmoids that in the limit as n goes to infinity become a step function, which switches from 0 to 1 when x goes from less than k to greater than k. Each increasing Hill function has a corresponding decreasing Hill function, which replaces the numerator by 1. And that gives you a sigmoid that decreases, again, with a value of a half when x is equal to k. And so we're going to use those rate rules, those empirical rate rules or phenomenological rate rules a lot as we go forward in the class. There are all sorts of issues to consider when you want to do these things. I strongly encourage you to look back at Herbert's textbook, Systems Biology, Introduction to Pathway Modeling, and some of his other textbooks that go into detail about some of the different forms, especially for multiple variables that are possible. But I would say that there's a standard best practice for this, which is if you have to come up with a rate law, you should always think about the following things. The first thing to think about is at the lower the limit of your variable, your parameter, what happens? Always start at 0. Is my value 0 or non-zero at 0? Potentially, it could even be infinite. And then ask the question at 0, is the slope 0, positive, or potentially infinite? Although those cases aren't so common. Then you switch to the other limit of large value. If I have a lot of T cells, if I have a lot of virus, what happens? And there I have the question, is the value 0? Is it finite and bounded, or is it infinite? And again, what's the slope at infinity? Is it 0, finite, or positive infinite? And those are really very constraining, especially if you know that your function is monotonic. It's either smoothly increasing or smoothly decreasing. Pretty much that answers most of your questions. The one other thing that you might ask, is there some other place where you know something about what's happening? For example, in the Hill function, you know that that inflection point, that half maximal point k, x equals k, is special. And so it's worth thinking about what happens at that point as well. It winds up that provided you have the right limiting behaviors, the details of how you get between those limiting behaviors tend not to be that important. They may make a 5%, 10% change in the results, but they're not going to change the results qualitatively. And so for most of the modeling we're doing, provided you get the limits right, everything else will come out pretty well. And we'll see that in what we're doing in the next section. Okay, now I want to move on. I'm already way over time, so I better go through this a little faster than I have been, is the viral load results. What we got was an initial delay, exponential increase, and now slow exponential decrease. I want now to consider why we're getting clearance. And the clearance is happening because of the adaptive immune system. And the adaptive immune system is a relatively complicated set of processes. In particular, the infected cells release a pro-inflammatory cytokine, and there also are what are called antigen-presenting cells, APCs, that actually grab pieces of dead infected cells from the tissue and crawl to the lymph nodes. And that crawling takes a couple of days. In the lymph nodes, they attach to T cells that are sitting there, and they stimulate the proliferation of those T cells. And those T cells come back, and those T cells have specific recognition molecules on their surface that recognize cells infected with the virus and the virus. And those cells, CD8 plus T cells, then come in and very specifically and effectively kill the infected cells. And this is what gives rise to that rapid clearance later in infection. And the delay until that rapid clearance is happening is coming about because it takes time for the antigen-presenting cells to get to the lymph node. And once they're there, it takes time for the T cells to replicate. So what we're going to do is we're going to build a model that includes these features. The first thing we're going to say is that there's a production of cytokine in the tissue, cytokine signal. We're going to find that this doesn't make a big difference now, but we're going to need it later on. And so we're going to say that our I1 cells and our I2 cells produce cytokine, an immune signal, and we're going to assume a linear production rate. And we're also going to assume that that cytokine has a lifetime. In this case, our numbers are pretty arbitrary. I will assume that the cytokine has a lifetime of about 12 hours. The production rate is something here that we can rescale. We could actually use a number 1 if we wanted to, and so we will. We don't have any experimental measurements, for example, of IL-6 levels. If we did, we could actually calibrate them. Okay, now we can put that into our equations and run it. And in this time, instead of asking you to do that by hand, I would ask you to skip down in our deck to compartment 84. Can everybody go to 84? Instead of taking the time to have everybody type it, I want to jump down to 84. So let's run down to 84 and run it. And can I ask people if they were able to get that to work? So find cell number 84, in which I've added the production of the cytokine. What I see is, at least for the parameter values that I picked here, the cytokine level tracks the level of virus very closely. And that's why I said I don't really need it. We're going to discover when we do cytokines in the cellularized form that it makes some difference, which is why I wanted to put it in explicitly. But for the moment, we're going to live with that as essentially a variable that's tracking one of the variables we already have. Okay. The next thing that has to happen, and let me hide that because there's a term that needs to be edited, is that the antigen presenting cells, which are created at the same time the cytokine is, have to get from the tissue to the lymph node. And we're going to assume that there's a transit time where the cells in the tissue give rise to cells in the lymph node. And this is a little bit dodgy, I have to say, in terms of the way we wrote it. We're going to say that the cytokine in the tissue leads to antigen-presenting cells, which we're calling CL, in the lymph node. The L stands for lymph node. with a rate that's proportional to the amount of cytokine in the tissue. And we're going to assume to begin with that it takes about 2 days for this signal, this antigen-presenting signal, to get to the lymph node. That is, the rate is about a half per day. We're also going to assume that once the signal gets there, once the antigen-presenting cells get to the lymph node, they last for about 2 days there. And so we're going to have an equation for CL by dt that is Kc times C, where C is the concentration of cytokine in the tissue, minus Cl times Cl, which is the rate of decay of the antigen-presenting cells in the lymph node. And I'm going to skip the exercise here. I'll just say that we have some rethinking on our own part about what that signal in the lymph node meant. And so you'll see that the word cytokine is used instead of antigen-presenting cell. So the terminology was a little bit unfortunate. But if we look at the level of CL in the lymph node, it still tracks. Nothing very exciting happens. I'm not going to have you do that one. But now something more interesting happens, which is those antigen-presenting cells in the lymph node, that CL, causes the T cells that exist in the lymph node to go out of their quiescent state and to start proliferating. And so we're now going to add a model for T cells in the lymph node, and these T cells are going to replicate. And there's going to be a pair of components here. The antigen-presenting cells are going to promote the activation of T cells at a rate CL times PEL. We're going to assume there's essentially a limitless reservoir of possible cells to activate. And then once those cells are activated, they're going to reproduce themselves. And that's going to give us a term that looks like reproduction rate, which is 1 over the cell cycle time, times the number of immune cells, EL. We're going to assume that there's a saturation, a Michaelis saturation, so that these immune cells can't proliferate without bounds in the tissue. And we're going to say that the immune cell production is also dependent on the amount of antigen presenting cells. In this case, it really probably is more the cytokine level than the antigen presenting cells. We're mixing the cytokine and antigen presenting cells in our CL term. And here we really are pretty much guessing about what's going on. We're going to say that our KEL, the saturation for our immune cells, is about 1,000 in our lymph node, our simulated lymph node. We do know the cell cycle time, it's about a day. We don't really know what the recruitment rate of T cells by the antigen presenting cells is. It's small. We're assuming it's 10 to the minus 4th per day. And we're picking, except for the rate EL, these other numbers are guesses that we've picked to try to make things work. And so we're going to use an equation in this form. There are plenty of other saturation forms we could use. You might expect that, for example, that the rate of proliferation saturates in the amount of antigen signal, obviously the amount of cytokine signal or APC signal. We haven't put that in. And so this is why I wanted to introduce the idea of coming up with theoretical phenomenological rate laws. There are really many that we could put in here. But the basic observation we want to respect, which is how the immune system works, is that it takes time for signal to go from the tissue to the lymph node, and that takes a couple of days. Once that signal gets to the lymph node, there is exponential increase of T cells, and the time scale for that exponential increase, the doubling time, is about a day. It could be 12 hours, it could be 2 days, but it's on the order of a day. And you can produce a lot of T cells in the lymph node, but there is some limit, and so there is a saturation K. And that rate of production has to be dependent on the signal coming from the tissue. If there's no signal coming from the tissue, you don't get any production. And so the linearity in CL is coming about because if there is no signal, we don't want there to be any T cells. Okay. So we can now put those in. And again, to save time, I'm not going to ask you to run it, type it all in, figure it out on your own. We can jump down to cell number 92, which has that in it. And I'd ask you now to run cell 92. The first three lines are going to be identical to the ones we've had before, but now we can look at the bottom, and the bottom is how many T cells we have as a function of time. And we see that the number of T cells starts out low, doesn't change at all till 2 days, and then it increases actually quite linearly, but quite rapidly. We wind up with 10 to the 10th T cells at the end of 10 days. Far too many, by the way, but that's a reasonable thing. Is everybody able to run that cell for the model? Again, this would be running cell number, sorry, I said 92, so it's 44. People have it? All right. Okay. Now, we have to keep tracking our innate adaptive immune system. Now we have to get the cells back. We've created our T cells in the lymph node. They now have to get back to the tissue. In reality, they probably get back reasonably quickly if they're going through the blood. If they go through the lymph, they probably take about as much time to crawl back as the antigen-presented cells took to go. And so we're going to assume that it takes about 2 days. And so we're going to now have an equation that takes our B cells out of the lymph node and puts them back in the tissue. And once they're in the tissue, they also have a lifetime. And we're going to assume that they live for about a day in the tissue. All of those numbers are reasonable, but not set in stone. But the lifetimes we're assuming are pretty reasonable. And we can run that model here. That's this one. That's number 45. And you can see now that our population of T cells in the tissue, which is E here, starts low. At 2 days, it increases to a maximum of a lot, probably more than we should have, like several orders of magnitude, and then gradually decreases again. And there's a question, why didn't we use a mass conserving equation for EL? So I guess the question is for which term in EL? The answer is that when cells divide, you get more cells. And so cell division is intrinsically not mass conserving if what you're looking at is the number of cells. If what you're looking at is mass, then of course the cells are taking in glucose and other nutrients and oxygen and turning it into cells. But the number of cells is not conserved in cell division. Good question. Now, the last thing that we have to do to get our adaptive immunity to work, and that is that our immune cells have to kill our infected cells. And so now we're going to say that the immune cells that have come back to the tissue are going to kill the infected cells. And we had this argument that we did earlier about the fact that that's rate limited. If we have a lot of infected cells and a few immune cells, we can't kill too many infected cells because it takes time for each immune cell to kill the target cell. In this case, we're picking a particular rate law, and that particular rate law that we picked is saturated in the number of infected cells in I2, but it has a slightly different form. Instead of being I2 divided by E in the denominator, we have I2 plus E in the denominator. And one could try both of those forms and see which one makes sense. And so we're going to now say that the rate of killing of the infected cells is proportional to the number of I2 cells normalized by this Michaelis function. And we have E times I2, that was that X times Y form that we looked at before, divided by K plus E equals I2. That was one of the combination forms we looked at as a possible way of doing combined saturation. As I mentioned, when you have more than one variable in a saturation equation, there are a lot of different structures. And so we should probably be exploring the consequences of different structures when we go. Here we picked parameters that give us sensible results for the parameters at hand. Those parameters probably don't have a biological meaning in this case because the number of T cells we're simulating is too big. If we rescaled the number of T cells to be more appropriate, for example, by having a faster decay term for the EL, then we would have to rescale these parameters as well. So the first parts of this, we actually had pretty good experimental data in terms of rate laws to go off of. Here, we're essentially trying to fit the result without asking in too much detail why the parameters have the values that they do. And we wind up with a full model like this. We have a model of the tissue in which you have initially uninfected cells becoming infected by virus. Those infected cells produce a signal which disappears after some time. They also become virus-producing I2 cells here. The virus itself can decay. The I2 cells can die directly because of viral production and innate immunity. There's a signal that's sent by the tissue related to the cytokine level and antigen presentation that goes to the lymph node. That signal in the lymph node decays. It also promotes production of adaptive immune cells. Those adaptive immune cells come back to the tissue. They disappear after a while, and they also promote the production, the death of the infected cell. So we have a full model then of that. That's here. Everybody try to find that model. Were people able to do that? Everybody find that cell? Number 46. It's got this picture in front of it. And the heading is putting everything together. We're looking for it. Okay. So now if I look at my viral load curve, I finally have what I wanted. I have my latency. I have my exponential increase in saturation. I have my slow decay, and followed by my rapid decay with clearance at day 8. And so we cheated a little bit in the sense that some of these parameter values are coming because we know what answer we want. That happens a lot in models of this kind. And we could definitely argue about some of the decisions we made in terms of saturation. But we do have probably the simplest possible model of the adaptive immune system that respects the fact that it takes time for the signal to go from the tissue to the lymph node. It takes time for the exponential increase of immune cells in the lymph node. Those immune cells in the lymph node take time to get back to the tissue. And once they're in the tissue, the rate at which immune cells can kill is limited by the amount of time it takes an immune cell to kill a target cell. All of those things are going to become much more interesting when we move into a cellularized version of this model, where we actually have explicit immune cells crawling around doing their work. And so the key result here was that we could at least conceptually reproduce without too much effort a simulation that produced the viral load curve that we wanted. There are a bunch of exercises that we could do based on this. I don't want to go through too many of them, but let us look at just one exercise here before we finish up. And we could do this, for example, by doing a parameter scan on some of the parameters that we think are very important. One of the parameters that could be important is the amount of time it takes for the signal to get from the lymph node to the T cell, from the tissue to the lymph node. That would be KC, capital C, KC here. Why don't we try doing one of those parameter sweeps? So to do that, I can go back. You can probably write it by yourself faster than it will take me to grab that parameter sweep. Here's my little parameter sweep code. Nothing fancy. I'll grab that parameter sweep code, and I'll come down here, and I'll put it in and see what happens. So in this case, I'm going to try changing the time scale for the virus, for the cytokine signal and the antigen presenting signal to get to my target. So let me do that. I'll say for P in range, let's say that it takes somewhere between 1 day and 7 days to get for the signal to get to my lymph node. So that would be KC. I'm going to set KC equal to 1.0 divided by, I have to use float. Float of P. And now I'm going to run here and see what happens to my virus. All right, let's try that. Good. So in this case, I get exactly what I would expect, which is the following. This is for that delay, for that KC being large, KC being 1, I get the curve that I just had. If I make the time to get to the lymph node longer, it slows down my immune response. And so the time to clear goes up. And I can make it visible if I increase the time my simulation runs a little bit, make it 15 days instead of 10 days. And I see that, I see that I continue to clear the virus, but the time to clear the virus goes up as that delay goes up. As you get older, that delay goes up. So if you're young, the clearance is faster than if you're old. So that's actually rather an interesting result. What if I change the rate at which my T cells kill my target cells? What was the number for that? The killing efficient rate was D2 here. DEI2 here was 0.12 initially. Let's multiply that by our result here. So in this case, as I increase P, my killing efficiency goes up. What do you think is going to happen? In this case, if I have my initial value, I had my clearance here in 8 days. As I increase the rate at which my T cells can kill my target cells, I clear faster. Let's look at one last combination. What if I change the saturation rate? That's a little bit more problematic in terms of understanding what the parameter means. And that was this KEI2 number here. Let's try making that saturation bigger. The bigger that saturation is, the more effective my T cells are going to be at killing. So let's use that. Try that. Basically get the same result that I had before. The bigger that number is, the faster I kill. So I'll let people play a little bit with this. Why doesn't everybody just take 3 or 4 minutes to play with that and see what you find? And you can pick the parameter that you like to vary. As a homework problem, you could think about some other forms of these equations. For example, one in which the virus is used up on the reaction, or one in which the structure of the killing is different, or the replication law or the immune cells in the lymph node is different. It also might be interesting, if you can, everything that we've done has been predicated on this viral load curve for influenza in mice. I'd ask you if you can do some Googling to find some viral load curves for other viruses. Can this model replicate the viral load curves that you see for other viruses? Could you get monophasic behavior? Could you get triphasic behavior from it? If not, why not? If you can, why? What are the parameter values that you'd have to use to get that? And so the next thing we're going to do is we'll pass this model off to Josh, who will walk you through how to turn this into a CompuCell model and turn it into a cellular model. But before we finish that, let's come back and try everybody doing 1 or 2 parameter sweeps for a parameter that you might find interesting in this model, and ask the question, how does changing that parameter change the viral load curve? In particular, does it increase or decrease the maximum amount of virus? Does it increase or decrease the time at which the virus is high? Does it increase or decrease the rate of clearance or the time at which clearance occurs? So why doesn't everybody just take 5 minutes and play with this model? Because you want to understand a little bit about how this model works before you put it into a more complicated context. And so I'll let you do that, and I can answer any questions people have about the model And then as soon as we're done with this exercise, we'll go on and start putting it inside of CompuCell and running. So the code for the sweep again. Again, the code I wrote for the sweep wasn't very pretty. I just used the code that I had on hand. If you use a range, you can probably come up with a prettier code, NumPy. All right, there was another question. Let's come back to the question. There was a question. Oh yes, one thing that we could do quite easily is have the effector T cells kill the I1 cells as well as the I2 cells. Well, in this particular model, there are almost no I1 cells left by the time the immune cells come in. And so having the T cells kill the I1 cells as well as the I2 cells is not going to make a big difference, but we could certainly put that in. If we have the immune cells killing the I1s as well as the I2s, it looks like that. I don't see any change in the result. Basically, it's because the I1 cells last a very short amount of time around day 2. They're all gone by day 4 when the immune system starts kicking in. One thing that we could do, which would probably make a difference, would be to change that latency period. That latency was the I1 to I2 term, that was the K. If we make K smaller, which would correspond to a longer delay, that's going to have a relatively big effect on the result, I believe. So here, I'm resetting the K value to be K divided by float. Remember, smaller K means longer delay. And so I'm putting in a longer delay for the cells to start producing virus. In this case, the effect isn't huge. I'm actually a little bit surprised that it slows down the time of the viral maximum. It doesn't do much else. So with this model, one can play around quite a bit. The base model in terms of the linear forms is pretty well behaved. The forms of the saturation that we've used here and here are a little bit problematic. We've got 2 saturation terms. You could argue about whether there are additional saturation terms that are needed. But in terms of writing a quick and dirty model of the adaptive immune system, it's not too bad. And so for that, if there are any other questions before we stop and turn it over to CompuCell? Okay. If people want to play a little bit more, do you want to move on and put this inside of CompuCell? Okay, it looks like people are pretty well done. The exercises will be available. And so if people want to try this at home, maybe come back to us with a better model that fits more times the virus, that would be great. We appreciate it very much. Again, this isn't meant to be a definitive model of viral clearance. but it is meant to be a placeholder that you could use to think about how you might build your own models of viral things. Okay, so that's the end of module 1.5, which took quite a while. I'm going to turn things over now to Josh.